Good evening, everyone. Today we will start with this electromagnetic radiation and absorption spectroscopy. Okay. So, what I thought is that before going into the details of each and every spectroscopic techniques, we need to understand the mechanisms, how this absorption spectroscopy or the emission spectroscopy they work. What is the underlying mechanism of within these spectroscopic techniques? Okay, so this will give you an understanding, better understanding about the subject when we will be going into the different spectroscopic techniques. Okay, so when we talk about spectroscopic techniques, these the spectroscopic techniques they include the use of electromagnetic radiations. Okay, now what are electromagnetic radiations? Electromagnetic radiations they are basically synchronized oscillations of electric and magnetic fields. Okay, that means they have a synchronized fields which are basically the electric field and the magnetic fields which are moving together in a synchronous manner. Okay, so due to this what you call reason, the electromagnetic the radiations they are also regarded as transverse waves. They are also regarded as transverse waves. Now, what happens in transverse waves? Can anyone tell me what happens in transverse waves? In a transverse wave, what happens is that suppose you have a pond, and in the pond, suppose this is the pond, and in the midst of the pond, you have thrown a stone. Okay, so as soon as you have thrown a stone, you will see some ripples they are propagating. Now, if you see over here, there are two types of movements. So, what happens? The waves moves outside from these points. So, another movement, if you see over here, these lines which I have shown, basically they are crests and troughs. So, the direction of the waves is in all the direction, that's okay, but there is another movement where the water is rising, then falling, again rising, again falling. And if you see this blue line and the transverse wave at some point, at this point they are perpendicular to each other. Okay, they are perpendicular to each other. Now herein, when we are talking about electric field and the magnetic field, what happens is that we are having in the electromagnetic radiations, we are having electric movement which is happening in the if you consider this as the x-axis, the upper one as the x-axis and this lower one as the y-axis, then in the x-axis you are having the electric field which is moving. Okay, whereas our magnetic field they are moving in the which is marked by these red lines, they are moving in the y plane. Okay, and if you see the x plane and the y plane, they are perpendicular to each other. Hence, the electromagnetic radiations they fall under the category of transverse waves. Okay. Now, examples of some of the electromagnetic radiations they include radio waves, microwaves, infrared waves, visible or light, ultraviolet rays, X-rays and gamma rays. One of the important property of each of these electromagnetic radiations is that they have three types of energy components. Okay, so they have their internal energy component, they have momentum when they are moving, and they have angular momentum. Okay, next, when these electromagnetic radiations they interact with some matter, then what they do, they impart the above quantities to the matter. What do you mean by above quantities? Above quantities means the energy, momentum, and the angular momentum. So all these types of energies, they are being they are being transferred, partially transferred to the above to the material. Okay, and in what way these energy components are being transferred to the material, that property it is being explored in the spectroscopy. Okay, that property is being explored in the spectroscopy. So from this slide, what is the gist over here? The gist is that we have electromagnetic radiations which are used in spectroscopy. And what are the electromagnetic radiations? They are basically transverse waves of electric and magnetic fields. Okay, and some of the common examples of the electromagnetic waves include electromagnetic radiations include radio waves, microwaves, infrared waves, light waves, then ultraviolet rays, X-rays, and gamma rays. And all these have some energy. And when these radiations they interact with the matter, they transfer an amount of energy to those matters, and how much energy or how much energy is being transferred to the molecule or the matter, that property is being explored in the field of spectroscopy. Okay. Now this is the electromagnetic spectrum which we have. If you see, we are having increasing wavelengths. Okay, we are having increasing wavelengths. So first we have gamma ray. So when we have gamma rays, it is having the highest frequency, because if you see, if the wavelength is increasing, your frequency decreases. The frequency increases in the opposite side. Okay, so when your wavelength decreases, your frequency increases, and vice versa. Okay, so when we start from the left, we have gamma rays, which is having the smallest what you call smallest wavelength. Okay, and then as we move on towards the right, we have X-rays, then we have UV region, then we have visible spectrum, then we have IR, then microwave, FM region, radio waves. This total is the radio waves. Okay, FM and AM, and then we have long radio waves. Okay, since we are having the smallest lambda in this region, this is up to UV. So what we said, the frequency is high. Now if the frequency is high, that means per unit of length we will be having more number of photon components. Okay, that means when your frequency is very high or your wavelength is short, these waves they have high energy content. Okay, and hence these rays, usually the gamma rays and the X rays, they are regarded as high energy radiations, high energy radiations. In the similar way, when we come towards the what you call increasing wavelengths or the decreasing frequency in the regions, this IR, microwave, and all these things, they are regarded as low energy radiations. Okay. So we have on our left hand side, we have high energy radiations. On the right hand side, we have the low energy radiations. And then in between, we have the visible spectrum. And in the visible spectrum, we have these colors. Okay, violet, indigo, blue, green, yellow, orange, red. So we have the Vibgyor. Okay. So all of this, all of us know, right? Next, move. So if you see, if you leave this region, we have the ionizing radiations. These are these gamma rays, hard X-rays, soft X-rays, and extreme ultraviolet. Why ionizing? They have very high. Sorry, let me change the color. They have very high energy. Okay, and when these gamma photons or hard X-ray photons or even the soft X-ray photons, they interact with the cells or the atoms of within the cells or whatever you tell. When there is a radiation like this, they can strike off the electrons from here. Okay, and that can lead to the absorption of the what you call of the photons of the radiation photons within the human body. Okay, and due to this, what is happening? The electron is moving out, and your atom, it is becoming charged or ionized. Okay, so hence these rays, they are regarded as ionizing radiations. They have the capability to interact with the atoms, and they have the capability to um, gives a sufficient amount of energy to those electrons so that they move out of the atom or the molecules and make the atom or the molecule an ionized entity. And due to that reason, these radiations, they are regarded as ionizing radiations. And on the right hand side, if you see energy per photon, so what we have in the energy per photon, 1.24 mega electron volt. Okay, 124 kilo electron volt, 12.4 kilo electron volt, 1.24 kilo electron volt. Okay, then we have 124 electron volt. Slowly see, there is a reduction in the energy per photon. Okay, right, and these are the wavelengths and these are the energies. Okay, then herein we come to this near ultraviolet, near infrared, then we have mid infrared, far infrared. Okay, this region, these are not ionizing, and then we have the microwaves and the radio waves frequencies. When we talk of spectroscopy, electromagnetic radiations, they play an important role in the spectroscopy, and some of the common electromagnetic radiations which have been explored in different types of spectroscopic techniques include X-ray, ultraviolet visible, okay, infrared radiations, microwaves, and radio waves. Okay, so when we talk of X-ray, if we use the source as the X-ray, then it is regarded as X-ray absorption spectroscopy. If we are using ultraviolet and visible light, then it is called UV visible absorption spectroscopy. And in most of the labs, you will find this UV visible absorption spectroscopy is there everywhere. Okay. And so we have both UV, in the UV visible spectroscopy, we have both ultraviolet radiation source and the visible sources. Then we have infrared absorption spectroscopy. Then we have microwave absorption spectroscopy. Then using the radio waves, we can have two types of spectroscopic techniques. The first one is the electron spin resonance spectroscopy, and the next one is the nuclear magnetic resonance spectroscopy. Okay, so these are the different spectroscopic techniques which employs electromagnetic radiations for the analysis of the different compounds or analytes. Okay. Now, basics of spectroscopy. Now, what is that? The first thing is that I talked about absorption. Okay. So, if you have a matter, we make a photon. I'm not talking about any specific photon. It may be X-ray photon, it may be light photon, it may be UV photon, whatever. It falls on the matter M and it can absorb some amount of these photons over here and some will be ejected out. Okay. So what is happening over here? It is coming with a, say, with an energy E, and as soon as it interacts with the matter, its energy is reduced. It comes out, it reduces the speed of this photon. Even though it reduces the speed of the photon or the energy of the photon, because it is absorbing some amount of the energy, the rest of the photons are being emitted. Now the photons which are emitted, they have low energy. Okay, they have low energy. So on the left hand side we have high energy photon, and when they enter into the matter system and interact with them, their energy is somewhat reduced and they passes out of the material in such a fashion that the photon which is exiting, it is having lower energy. Okay, it is having lower energy. Okay. A simple case or the example of this one I can give you. Many of you must have gone for X-ray radiography. Okay, so in the X-ray radiography, what happens? There is a source S, okay, which generates X-ray and on the other hand you have an X-ray plate. Now this person is skinning. Now you have this source which generates some X-rays. So it passes through this and it what do you call it? The X-rays are then incident onto the X-ray plate. Now there are two things. We have soft tissues, which are soft materials which interacts with the X-rays in a specific manner. Then we have hard tissues like bones which interacts with the X-rays in a different manner. So depending upon how the X-ray photons are interacting with the soft tissue and the bone tissue, we get an image on the X-ray plate. Okay. Now suppose under the same conditions, if I bring another person who is say 10 times fatter than me, then you will find that the energy of the photons which are reaching the photographic plate, it has reduced. Why? Because now since the person is 10 times fatter, he is having a lot of soft tissues, and it is basically the cumulative interaction across the length of this material, which is playing an important role in the spectroscopic technique. Are you getting my point? Suppose I have a matter M of length L, and then I have the another object, not say object 1, not matter. Say matter is same, but say I am having an object 1 which is having a length of L, and then I have another object 2 which is having a length of 2L. So what will happen? The interaction with the matter will be lower when I am having O1, whereas the interaction of the matter with the rays will be higher when I am having 2L. Okay, so it is not only the matter which is playing a role, but it is also the length of the object which can also regulate the quantum of energy reduction which is taking place when you are making a photon incident onto the object. Okay, so am I clear?
Yes, sir.
Okay, good.
Yes, sir.
So next word, I have talked about a photon, right? Now one photon can have only one energy, right? Now when one photon is having one energy, that means it is a monochromatic radiation.
Yes, sir.
Okay, monochromatic radiation means one energy means it is having a particular frequency. Okay, and when it is having a particular frequency, one single frequency component, then it is called monochromatic radiation. Okay, so these are monochromatic radiations. We have considered this one. Now suppose when I am doing the spectroscopy, I may be interested in the full spectrum. Okay, so when you talk about UV visible spectroscopy, we talk about now the say wavelength ranging from 200 nanometer to 700 nanometer. So what we do in many of the cases, you must have seen that we go for the analysis in the full spectrum. Okay, we go for the analysis in the full spectrum. Suppose you want to find, you have been given with an unknown analyte, say X1. I gave you an unknown analyte X1, and I tell you, you perform the what you call quantitative analysis of this analyte. How will you do it? Because you do not know anything about this analyte X1. So how will you proceed? The first thing what we have to do, and yeah, I have told you you have the access of only UV visible spectrophotometer. Okay. So what is the first thing you will be doing? You will be making a solution of this X1, and you will be going for wavelength scanning. Okay. So why I need to go for a wavelength scanning? If you see, when I talked about this photon P and it is interacting with the matter M, suppose now we are considering that this length is same, so it is interacting with the M and it is getting out. Okay, its energy is reduced. Okay, that's fine. Now there can be two things. Suppose you must have seen the football. So if there is a free kick near the goal post, so what you do? You have a barrier. Okay. Now, if a person from the other team he wants to come in and wants to go through this, you will be giving them a higher resistance. On the contrary, if this person is from your team, you will allow him to pass through this wall quite easily. What I mean to say, the matters or the object what you are using, it may also have a differential liking for a particular energy system. Okay, differential liking means it may absorb a particular frequency component in a larger amount as compared to the other other frequency components. Okay, so what I said, it has liking for particular frequency components. Now, if you have a spectrum, say in the visible spectrum only I am drawing, you are having Vibgyor. Okay, so here you are having violet and here you are having red component. Okay, now what will happen is that if the matter is having a liking for a particular frequency component, after if you analyze these photons, which is now not a monochromatic radiation, you are basically changing this monochromatic photons, you are changing the wavelengths and you are looking into these aspects. Okay, so at particular wavelengths the matter will show some dark lines. Okay, now why these dark lines are there? These dark lines means there is no photon which is getting out of the matter. That means these photons, they are getting absorbed within the system. Okay, these photons, they are getting absorbed within the system. And when we go for this wavelength scanning, what we basically do is that we look into the wavelength, where x-axis is the wavelength, it is the independent axis, and on the y-axis we have absorption. So we look into, we'll be having something differential spectrums. Okay, now that means these black lines indicates that at a particular lambda 1 there is a complete absorption of the photon. Over here there is a reduction in the, suppose corresponding to this one, there is a reduction in the absorption, but still it is absorbing bit higher than these basal level areas. Okay, so in this fashion you can find out which is the highest peak, and then you can analyze the analyte x1 quantitatively around this wavelength. Okay, around this wavelength. Okay, now this pattern where you are having black lines, these are called lines of patterns. These are called lines of patterns, and these lines of patterns, they are regarded as or they are used for functional group identification and chemical structure determination. Okay, and chemical structure determination. Okay, so this is all about the absorption. You are making the photon, you are incidenting a photon onto a matter, then matter is absorbing some amount of photon and it is releasing some part of the photon on the other side, and you are analyzing those photons, and these photons, they have different wavelengths. Okay, and at different wavelengths you are trying to find out how much absorption has taken place. Okay, and from there you find out these lines of patterns. So these lines of patterns, they are basically, you can say, fingerprint for each and every molecule. Okay. Suppose there are many drugs like salicylic acid. Okay. It will be having a particular lines of pattern. If you talk of say paracetamol, okay, it will be having another lines of patterns. So whatever the molecule you talk of, there will be different lines of patterns, and from the lines of patterns, if you match two lines of patterns, then you can tell that this is the chemical, this might be the chemical structure of this molecule or whatever. Okay. And even there are some functional groups which can help you in the identification, especially it happens in the case of IR spectroscopy. We will see that later on, that IR spectroscopy, it helps us in the identification of the functional groups within the compounds. Okay. So this is what we call this is what is there in the absorption spectroscopy. So at the molecular level, what is happening? You are having an photon energy. It is being incident onto the molecule, which is present in the ground state. So the electrons from here, it absorbs the energy from here and it goes up to the E2 level. Okay. And how much energy has been absorbed? So as you go from here, some of the energy, it will be passed through this molecule, and this what you call, whatever the residual components which have passed through the molecule, they are those photons are analyzed for the energy content. So this is absorption spectroscopy. Now the next thing is emission. Okay. So what is emission? The internal energy of the molecule is converted to electromagnetic radiations. Okay. The internal energy of the molecules is converted to electromagnetic radiations, and this phenomena is used in emission spectroscopy. So I will tell you what is happening. So suppose you have made the photon incident, it has gone to the upper level. Okay, you forget this now. Now your electron, it is in the excited level. Okay, now it is at a higher level. Okay, if it has to come down to the basal level, it has to release some energy, and if these energies, how they will release? They will be releasing some photons over here also. Now if these photons, they are in the say UV visible region, then you can get a UV or visible photons. If it is in the X-ray region, then you will get X-ray photons. Okay, so let us consider that the energy what is being released is a visible are visible photons. So it will release some visible photons from here. Okay. Now if you try to look into the energy content or the frequency component of these photons, then you get the emission spectra. Okay, it is similar to the absorption spectra, but there is a difference. Okay, but there is a difference. The difference is that when you talk about the fluorescence, yeah, or you talk about this absorption spectroscopy first. Let's talk over here. If you remember correctly, I said when there is a higher interaction, there will be absorption over here. However, if there is at the other frequency components, if there is no liking for those frequency components, they will be passing all throughout and you'll be getting some black lines, right? you will be getting some black lines of patterns. Good. Here also you will get some lines of patterns, but if you see here, in actuality, you are not having any external radiations. This is a secondary stage. Are you getting my point? In the first step, in the absorption spectroscopy, you are exciting and how much is coming out you are measuring. In the second case, in the emission, you are doing this stage. That's why these electrons, they are going to the excited level, but you are not taking this incident radiation this thing into account. So that is totally missing. So there is nothing over here. Okay, so here you will be having brighter region, and within the brighter region you will be having dark lines. On the contrary, in the emission spectroscopy, you will be having darker region. Okay, you will be having darker region, and within the darker region you will be having some bright lines. These are also lines of patterns, but in the absorption spectroscopy we are having darker lines over a brighter region, whereas in the emission spectroscopy we have brighter lines over a darker region. Are you getting my point? Am I clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Good. Now, ground energy level, it has which is given by Eg, ground energy level. So it has rotational energy, it has vibrational energy, it has electronic energy. Okay, so rotational energy is given by Er, Ev, E. Okay. When a wavelength of natural frequency strike a molecule, so what do you mean by the natural frequency? I told you that the matter may have a liking for a particular energy or the particular frequency photons. So that frequency for which the matter is having a liking is called natural frequency. Okay, so a matter may have, or a molecule may have, different liking for different frequency photons, and hence it is regarded as natural frequencies. Okay, so they strike a molecule, the molecule is raised to the excited level, state level, and usually this delta E, it is given by 286,000 kilocal per molecule. Okay, now these molecules, they return to the ground state in 10 to the power minus 9 to 10 to the power 8 seconds, and during this they releases the energy, okay, and that energy is being measured in emission spectroscopy. Okay. Yeah, so we are getting into another thing. So this is ground state energy levels. In that we have rotational energies V0, V1, then V1, V2. Now we have the vibrational energy. So these are the different energy levels. When we excite the electrons, then they go to the excited level, that is V-2, V-1, V-0. So in this excited level also, if you see, you are having different levels. Okay. So this is the schematic diagram, schematic energy level diagram. Okay. Now what does this say? So if you see, there were three levels, V0, V1, V2. Okay. Sorry. So if you say this lowest one, it is for the sigma electrons. This sigma, it means electrons. Okay, pi is pi bond electrons, sigma bond electrons, and n is non-bonding electrons. Okay, so if you see n to pi star, there can be a transition between from n level to the pi star. Then pi to pi star, there can be a transition. Then n to pi star, pi to sigma star, then sigma to pi star, sigma to sigma star. Okay, as we go from here to here, the amount of energy which is required to send the electrons to the excited level increases. Okay, so that means if you need to send a non-bonding electron to the pi star antibonding electronic state, then you will be needing a lesser amount of energy as compared to the stage where you want to send the sigma electrons to the sigma star uh, state. Okay. Now let's see what are these. These are the types of electrons which I have told. The sigma electrons, they are found in fully saturated systems like alkanes. Okay, they are found in fully saturated systems like alkanes. Okay, and a large amount of energy is needed for their excitation. Usually do not show any absorption in the UV region. In some cases, sigma to pi star transition can give rise to hyperconjugation. Okay. Then N stands for non-bonding electrons. Okay. So valence electrons do not participate in chemical bonding, and they are principally located at atomic orbital of nitrogen, oxygen, sulfur, and halogen as lone pairs. Okay. And these bondings, they usually give rise to N to pi star transition in the UV region. And lastly, the pi electrons. These are the most mobile electrons, and they are due to the atomic p orbital electrons. Okay, they are found in unsaturated compounds in multiple bonds. Okay, and pi to pi star transition is the most common transition which happens in the UV visible transition. Okay, so pi to pi star is the major thing. Okay, now the absorption spectra, due to electronic level transitions in the groups which are present in the molecule. Okay, now there are certain what you call, within a molecule there will be certain group which can absorb the radiations, and which results in this absorption spectra. These are regarded as the chromophores. These are regarded as the chromophores. So chromophores are the what you call, are the functional groups which are present within a molecule which is responsible for the induction of the absorption spectra. Okay, then so they are the major culprit for the absorption of the radiations. Additionally, there are some auxochrome. What are these auxochromes? These auxochromes, they do not do anything on their own. Okay, so if you see, they do not absorb radiation at wavelengths greater than 200 nanometer. So they appear as if they are very good student, they are not disturbing the class and something like this, but they are the disturbance creators, but they do it in a silent way. Okay, so what it does is that if you are having the chromophore, they will modify and shift the positions of the absorption band. Modify means modify the absorption capacity. Suppose initially the chromophore was absorbing say 100 photons. Okay, now it can either result in the increase or the decrease in the number of photons that will be absorbed, or it will shift the absorption band either to the higher wavelengths or to the lower wavelengths. Okay, and these are mainly what you call responsible for the spectral shifts. Okay, so when you will go for some say analysis of any analytes, suppose you have made a what do you call, you have made a molecule, okay, and it is having a from a base molecule, say base from a base molecule A, you have made a molecule B, okay. So the backbone of both the systems are same, but on the B you have an additional group which itself is not a chromophore, but what will happen, this so if it is not a chromophore and it is resulting in the spectral shift, then it is an auxochrome. So the spectra of A and B will be similar, but there will be spectral shift either to a higher wavelength or to a lower wavelength, and depending upon what is the quantum of the auxochrome you have included, it may vary. Okay, suppose you are having a peak, absorption peak at say 400 nanometers. Okay, now the inclusion of the auxochrome may shift the peak either to 405 nanometer or to 395 nanometer. Okay, so this shift either to the higher wavelength or to the lower wavelength, it is regarded as spectral shifts. Okay, so absorption bands and electronic transitions for common chromophores in alkenes, uh, it will be something like this. It is ethylene. Then you have maximum at 165 and 193 in alkenes. You have unsaturated bonds. So what is the transition, electronic transition which should take place? Pi to pi star. Then we have amine. In amine you have aniline cation, and maximum and minimum this thing absorption bands would occur over here in this region, and again pi to pi start here. Okay, so similarly you are having pi to, mainly see pi to pi star electronic transitions, and some of the n to pi star, because it required the lowest energy. If you see, it requires the lowest energy, even though you are using the non-bonding electrons, it requires the lowest amount of energy. So in some of the cases you can see the n to pi star transition also. Okay, and these are some of the chromophores. So you have to remember these chromophores and what is the chemical structure and the examples. There is no need to remember this thing, and it is better to remember these electronic transitions of whatever the electronic transitions have been given over here. So you have to write down this thing. You need not to write down these wavelengths. Okay, but this is just for your information. Now, yeah, spectral shift. So what I was telling. Now, suppose we were talking about this thing. Say you have got a peak, absorption peak. This is the absorption peak, and here you are having at 400 nanometer. You are having this thing. Now, if this peak after the inclusion of the auxochrome it shifts towards the right, then it is called red shift, and if it shifts towards the lower wavelengths, then it is called blue shift. So if you see, we are talking about the shifting in the wavelength region. Okay, so if the peak shifts to a higher region, it is red shift, and if the peak shifts toward the lower wavelengths, it is called blue shift. Also, when you are adding up some these auxochromes, they may also alter the alter the nature, what I meant to say is that it may alter the nature of the interactions. Okay, and due to that, if the absorption of the peak is increased, then it is called hyperchromic shift because absorption is increasing, and if the absorption is decreasing, it is called hypochromic shift. Okay, hyperchromic shift means when the auxochrome, it results in the increase in the absorption spectrum, in the absorption value, and hypochromic shift means when the auxochrome is leading to the reduction in the absorption peak. Okay, so with this I conclude this topic. So I'll be happy if you have any questions. We still are left with 5 minutes. Anyone?
So, sir, in spectroscopy, how do we counter the effects of auxochromes?
You
Like, are
can't.
they always present, or
Yeah.
we cannot?
What do you mean by auxochrome? Suppose you are a polymer scientist. Okay, you want to make a polymer. So you have a say one of the most commonly used polymer is polyvinyl alcohol in many of the biomedical applications. Okay,
Okay,
now
sir.
you want to chemically modify that thing. Okay, when you want to modify the stuff, that extra element or extra group what you are attaching, it may be an chromophore. That means it will lead to the absorption of some of the components over there, some of the radiation components over there. Good. If it is not chromophore, or say, yeah, even if it is a if it is not a chromophore, you have another group which you have attached. Now what it is doing, it is not absorbing, but at the same time what it is doing is that it is playing with the absorption spectra of the what do you call, Hmm,
Polymer.
of the main polymer backbone. Okay,
Okay, sir.
so it itself is not absorbing. If you look into the monomer, you will find that it itself is not absorbing anything, but if you are adding it to one of the polymer, it is modulating the spectra of the polymer. It is something like this. Suppose there is a very old saying, which I don't believe that it is correct all the time, that if you stay with good IQ people, you will be, you will also be becoming a good thing. Okay. So the good people, if you see, they are not they will not if you are very, if there is a very studious person, he or she will not disturb you much. Okay, but if you go for a group study with that person, what will happen? He will definitely, if he is a good student, he will definitely help you out in improving your scores, grades, right? So basically you can tell them that they are auxochromes, so they do not disturb the other classes, they are just into their own studies, but if you go for help towards them, they will help you out and
Okay, sir.
your grades can be improved. Similarly, if you go to a person who is very mischievous, so he may modulate you to not to study whatever you are studying. So you will reduce your studying and your grades will be coming down. So they can be in other way an auxochrome. So they themselves are usually they do not have any effect. But if you bring them to the to other molecules or the polymers, they may have a they may shift the thing, they
Okay,
may
sir.
what you call, they may result in the alteration in the performance. Okay.
Okay, sir. Thank you, sir.
Welcome. Anything else?
No, sir.
Okay then.